Welcome back to Algebra. Today we're going to keep talking about group actions. In the previous video, we have defined what's a group action, and today we're going to be talking about properties of group actions. So just to recap, a group action is the following. We have a set X and a group G that acts on X, meaning that I can send elements of X to other elements of X via the elements of G. So that we call that a left action of G on X, and that's a map from G cross X to X that sends a pair of an element of G and an element of X to a G dot X. This is the element G acting on X, and it's going to be a new element of my set X. We have to declare two properties for this to be an action. The identity works as the identity. It sends X to X for every X, and the multiplication is associative in this way. If so, we say that X is a G set. Okay, so let me do a further definition. We are going to define orbits of elements about using the action X. So let X be a set. Let G be a group. And suppose X is a G set. In the future, I might just say X is a G set and avoid saying that X is a set, G is a group, and so on. And let X and Y be elements of X. We say that X is a G equivalent to Y, or we write that X and Y are equivalent in this way if there is some G in G such that X is G dot Y. So I can act on Y via an element of G and get to X. If so, then we say that X is in the orbit of Y, or that Y is in the orbit of X. We'll see that it's a symmetric relationship. And then we say the set of all G equivalent elements to X is the orbit of X, and we write it by G times X. That will be the entire orbit, or the orbit of X. So let me give you some examples of this. So here we've defined what it means to be G equivalent and what is the orbit of X. So again, the orbit of X will be all the elements that are G equivalent to X. So in fact, it will be everything of this form. Okay. So let's do an example. So for example, let S4 acting on 1, 2, 3, 4. Then what is the orbit? The orbit S4 times 1, so the orbit of 1. Well, if you write 1, 2, 3, and 4, then you can see that so it's the orbit will be every element that I can get to starting from 1. But for example, from here to here, I have, let's say, 1, 2, 3, 4. That's an element that goes to 2. From here to here, I can take the element, for example, 1, 3 goes to 3. And from here to here, there's an element in S4, which is 1, 4. It goes there. So you can see that everything will be in the orbit of 1. So the orbit of 1 is all of X. Okay, similarly, I can get from 2 anywhere. So the orbit of 2 is also X, and it's the orbit of 1. So in this case, there's only one orbit. Okay. How about let's restrict that and let's write a different subgroup. So let's think about the identity 1, 2, 3, 4, and 1, 2, 3, 4. This is a subgroup of S4, but it also acts on 1, 2, 3, 4 on X. And it acts how? Let's see where where each element takes 1, 2, 3, 4. Let's draw diagrams for the identity. So I'm going to, I guess, draw. I have 4 elements. So 1, 2, 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4. Let's draw diagrams for each element. So the identity just sends everything to itself. So 1 goes to 1. 1, 2 sends 1 to 2 and 2 to 1, and it leaves 4 and 3 stable. 3, 4 sends 3 to 4 and 4 to 3, but it leaves 1 and 2 stable. And then there is 1, 2, 3, 4, which sends 1 to 2, 2 to 1, 3 to 4, and 4 to 3. So these are the 4 possibilities. So then what is the orbit of 1? You can see now that 1 can go, 1 can go to 1, right? 1 can go to 1, or 1 can go to 2, or to 1, or to 2. So the orbit of 1 is only 1 and 2 and nothing else. I cannot get to 3 using this action of this group G on X. Similarly, the orbit of 2 is the same as the orbit of 1. The orbit of 3, I can get to 4, but I can't get to 1 or 2, and similarly for the orbit of 4. So those are, first of all, these are the orbits, and we say then that 1 and 2 are G equivalent, and 3 and 4 are G equivalent, while in here, every element was G equivalent to each other. Great. Let's do one more example. Here's another example of an action we saw. We were looking at Z modulo 2, which was just the identity and tau complex conjugation acting on the complex numbers. And then what we saw is that there's 2 types of orbits. So if alpha is a plus bi, then the orbit of alpha, the numbers that are G equivalent to alpha, is itself and its complex conjugate. There's nothing else that this action does. So, but now there are 2 possibilities then. If B is non-zero, then there are 2 elements in the orbit. There is alpha and what we call the complex conjugate. So there is A plus BI and also A minus BI. But if B is 0, so that A plus BI is actually a real number, then there is only 1 element in the orbit, and it's just alpha. Okay. All right, so now what I want to show is the following proposition. These orbits are going to be equivalence classes modulo what we call an equivalence relation. So let X be a G set. Then G equivalence is an equivalence relation. What does that mean? We need to check that equivalence is symmetric, that equivalence is reflexive, and that equivalence is transitive. So let's see all those 3. So let's prove those. Okay, so let's start with the reflexive property. So remember, by the way, recall that we say X is equivalent to Y if there is a G in G such that X is G times Y. Okay, that is G acting on Y is X. So reflexive means that we want to show that X is equivalent to X for all X. And that is true because there is an element, which is the identity, such that X is E times X, and therefore X is G equivalent to itself. So that proves that the property is reflexive. Let's prove that it's symmetric. So what we want to show is that if X is equivalent to G, if X is equivalent to Y, then Y is equivalent to X. So let's suppose that X is G equivalent to Y. And so there is some G in G such that X is G action Y. Then what I would like to do is actually multiply by the inverse of G on both sides. However, this equation is not an equation in G. It's not an equation in the group. These X and Y are elements. So this is not an equation happening in G. It's just saying that this element in the set X, the little x, and the set element Y are related via some action of G. However, I can try to see what happens if I sort of multiply by G inverse using the action. What is G inverse acting on X? Well, G inverse acting on X, I don't know, but I know what X is. X is G acting on Y. And since this is an action, this action is associative, so I can rewrite this as G inverse star G acting on Y. And now you see that this over here, that is happening in G. And we know that the inverse times itself is always identity. So this is the identity dot Y. And now I know that the identity acts as identity in the terms of the action, so this is just Y. Therefore, there is an element of G, namely G inverse, such that Y is G inverse acting on X, and therefore that means that Y is G equivalent to X, like we wanted to show. So this is reflexive and symmetric. So now let's prove that it's transitive. So it remains to prove that the G equivalence is a transitive relation. So now what I want to show is that if X is related to Y and Y is related to Z, then X is G equivalent to Z. So suppose that X is equivalent to Y and Y is equivalent to Z, then there are some G and H in G such that this means that X is G dot Y and that Y is some H dot Z. Okay, and therefore I want to eventually get to X is something in terms of Z, but I can do that because then I can simply plug in what Y is. This is Y is H times Z, or H acting on Z, and therefore now because this is an action, the action is associative, so this is G times H in the group acting on Z. There is an element in G. G is closed, so G times H is in G. So there is G times H, some G prime in G, such that X is G prime times acting on Z, and therefore we have proved that X is also equivalent to Z. So this shows that G equivalence is an equivalence relation, and whenever you have an equivalence relation, you can define the equivalence classes. So let's define that. Let X be a G set. So a set X with an action of G. The set of all equivalence classes of X with respect to these G equivalents will be denoted by, we're going to write X over G. Let me write that correctly so there's no confusion. We'll say X, essentially we'll say X modulo G, or X modulo G equivalents, or simply X modulo the equivalence for the set of equivalence classes. So let me give you an example to start. Let's start with the simplest example we've seen, which was S4 acting on 1, 2, 3, 4. Then what are the equivalence classes? We saw that the orbit of 1 is all of x. I get all of x back, all of 1, 2, 3, 4. So there is only one equivalence class. So x modulo this equivalence by S4, there's only one class, and that class is the class of the orbit of 1. Okay, we write that. Sometimes we'll write just the class of 1, meaning the same thing. The class of 1 would be every element in X such that X and 1 are G equivalent, which is, again, what we are denoting right now, the orbit of 1. So there's only one orbit. Let's see another example where there is more orbits and more equivalence classes. So we had this other group, 1, 2, 3, 4, 1, 2, 3, 4. This acting again on 1, 2, 3, 4 on X. What are the set of equivalence classes? Now there are two different orbits. There is the orbit of 1, which is 1 and 2, which is the same as the orbit of 2. And then there's the orbit of 3, 3 and 4, which is the same as the orbit of 4. So the set of equivalence classes, modulo, this is my G, so modulo G, the set of equivalence classes, there will be two sets of elements that are G equivalent. There is the class of 1, and then there is the class of 3. Okay, so now we have two different sets, and notice that X is partitioned as a disjoint union of these two orbits. Similarly, in here, this was not great news, but this is partitioned into disjoint orbits. There's only one orbit in this case. Here, though, there is two orbits, and X is partitioned as a disjoint union of orbits. That happens also in any set of equivalence classes. You can pick equivalence classes that are disjoint and then partition your set X as a disjoint union of equivalence classes. The same thing happened, remember, we would say Z modulo NZ as a quotient, as a Z modulo some equivalence modulo N. This was the disjoint union of the classes of 0 modulo N, union the class of 1 modulo N, union up to disjoint union with the class of -1 modulo N, and that partition all of, so these are the classes. The classes would be the set of these N elements, but what I wrote here is that the integers themselves are partitioned as a disjoint union of equivalence classes. Okay, one more example of this concept. Let's do again Z modulo 2, so the identity and complex conjugation acting on the complex numbers. What are the possible equivalence classes? We saw that there's two types. There is the orbit of an element is either the element, if the element itself is real, or the element and its complex conjugate if alpha is not real. So if you draw the complex plane, then there were pairs. Either this one is paired with that one via the action, or this one is just paired with itself, and the action just stabilizes it. So to get representatives of every orbit, I want to not get a duplicate. So I don't want these ones. I can just pick, for example, every element in here, including one in the real line, will be a representative of each element. So what happens then is that if I call this G, the set of equivalence classes, there is um, the orbit of alpha, one for every real number. This joint union, the orbit of alpha, one for every complex number a plus bi, with b bigger than 0. This is what we usually call the upper half plane. Many times we just call it H, like that. Oops. So that's not what I meant here. So I meant a complex number with positive imaginary part, and when this is the upper half plane, so it's all of this, including the real line. That is a set of representatives for every type of orbit of the complex numbers modulo the action of conjugation. Okay, so now let's talk about fixed points and stabilizers. So we're going to define a few more concepts that have to do with this sort of like discrete dynamic system interpretation of the action of G. So let X be a G set. One, let's include here the definition of orbit, just so we have them all in one place. Let X be in X. The orbit of X under G is, again, we either write it like this or O sub X. And those are other elements of X, so that you arrive to using the action of G. And an orbit is a subset of X. Two, let G be in G, the fixed points under the action of G is the set. So these are going to be the points that G acts trivially on. So those are, we're going to denote xg, and those are again x's such that g dot x is x, and this is again a subset of x, elements of x that are fixed by the action of G of a particular element, little g. And third, let X be in X. The stabilizer of X is those elements in G that leave X fixed. So the stabilizer is going to X be denoted by G sub X, and those are elements in G such that G times X is X. And this is a subset of G. So let's again see an example of all of these concepts, the orbit, the fixed points, and the stabilizer. So let's see some examples. For example, S4 acting on 1, 2, 3, 4. Let's see, first of all, what is the orbit of 1? If this is x, the orbit of 1 is all of x. What is, let's see, for example, what is x of 1, 2? So these would be the elements in X that are fixed by the permutation 1, 2. The permutation 1, 2 sends 1 to 2 and 2 to 1, but it fixes 3 and 4. So these are the elements 3 and 4. And finally, what is the stabilizer of 1? So now the stabilizer of 1 are going to be those elements in S4 that stabilize 1. So it will be just any permutation, sigma in S4, such that sigma of 1 is 1. Now, there are a lot of elements in here, and in fact, for example, what elements are in there? So it just has to fix 1. So for example, 2, 3, or 3, 4, or 2, 4, those fix 1. The identity fixes 1, right? And then we have also things like 2, 3, 4, or 2, 4, 3. And it turns out that's it, because if we fix 1, now we can do all the possible permutations of 2, 3, and 4. So it has to be isomorphic to S3, but acting on the letters is the sort of like the symmetries of a set of 3 letters, but we are doing the symmetries on 2, 3, and 4. But the names of the letters do not matter, and I get something that is like S3 again. And one thing to notice is note that G1 is a subgroup of G of S4. Okay, let's do some other example. Let's take, like before, G to be 1, 1, 2, 3, 4, and 1, 2, 3, 4, acting on 1, 2, 3, 4 on X. Then we had before the orbit of 1 is 1 and 2. What about, let's take, for example, what is x of 1, 2 now? What elements are fixed by 1, 2? It's the same. 3 and 4 are fixed by 1, 2. What about what is the fixed elements by 1, 2, 3, 4? Notice that 1 is sent to 2, 2 to 1, 3 to 4, and 4 to 3. So nothing is fixed. So this is empty. There is nothing being fixed by that element. How about, let's find the stabilizer of 1. Here, the stabilizer of 1 will be those elements in my group that fix 1. 1 is not fixed by this. 1 is fixed, not fixed, fixed, not fixed. So this is 1 and 3, 4 in this case. And this, again, notice that it is a subgroup like before. Last example, let's do again the action of the identity and complex conjugation on the complex numbers. And let's see what is, so what is x tau? So what points are fixed by complex conjugation? Well, the complex conjugation fixed points will be those elements of the complex numbers such that complex conjugation of alpha is alpha itself, but the complex numbers that alpha is equal to its complex conjugate are precisely the real numbers. Now, if alpha is a complex number, what is the stabilizer of alpha? So what is G alpha? The stabilizer will be if alpha is not real, the only thing that stabilizes is the identity. Then the stabilizer is just the identity element. However, if alpha is real, then the identity and complex conjugation fixes it, so the stabilizer will be all of the group. And notice that, again, every one of these stabilizers is a subgroup, so that is something we will prove soon. One more example. Let me give you a little bit more exotic example. So let G be the subgroup generated by, or the subgroup that the elements are 1, 1, 2, 3, 4, 5, 6, 3, 5, 4, 6, and 1, 2, 3, 6, 5, 4. This is a subgroup of S6, and it acts on X, which is 1, 2, 3, 4, 5, and 6. Okay, you can check that that is actually a subgroup for the 4 of S6. So let's compute some of these things. What is X of 1? What are the fixed points by the identity? Everything is fixed by the identity, so I get X back. What are the fixed points by these elements 3, 5, 4, 6? 3, 5, 4, 6, they move 3, 5, 4, and 6. So the only things that are not moved are 1 and 2. What is X of, for example, 1, 2, 3, 4, 5, 6? Everything goes somewhere. 1, 2, 3, 4, 5, 6 are involved in the product of those disjoint permutations. So there is nothing in here. It's the empty set. What about some stabilizers? What stabilizes 1? The identity stabilizes 1. This element does not stabilize 1, but this element does, and this element doesn't. So we have one more in here. 3, 5, 4, 6 is in the stabilizer of 1, and that's it. Notice that this also stabilizes 2. So the stabilizer of 2 is also that. And what about X of, G. I'm looking for more G's. How about the stabilizer of 3? So the stabilizer of 3, notice that this does not stabilize 3, this doesn't stabilize 3, and this doesn't stabilize 3. So actually 3 only is stabilized by the identity. And similarly, 4, 5, and 6 are only stabilized by the identity, so all those stabilizers are trivial. And again, we have that every one of those is a subgroup of G. So let's prove the following. Let's prove that stabilizer is a subgroup of G. Proposition, let X be a G set, and let little x be in X. Then the stabilizer is a subgroup of G. Let's prove this. So first of all, let me remind you the definition of the stabilizer. Those are elements in G that fix, or the action of G on X fixes X. So let's prove that the identity is in the stabilizer. Notice that E acting on X is X because this is a group action. So by the definition of group action, and therefore E is in the stabilizer. E stabilizes X, so it's in the stabilizer of X. Great, so we have the identity. 2, let's prove that the stabilizer is closed under inversion. So let G be an element of the stabilizer. Then G dot X is X. So how about what is G inverse acting on X? Well, I know because G dot X is X, X itself is G dot X, so I can replace X by G dot X. And now because it is a group action, the group action is associative, so this is G inverse G acting on X, and G inverse G is the identity acting on X, which is X because it is a group action. And therefore, what we get is that G inverse fixes X, and hence G inverse is also in the stabilizer. Great, so the stabilizer is closed under inversion. And 3, suppose G and H are in the stabilizer. I want their product to be in the stabilizer. Well, let's see what happens if I do GH.X. The action is associative, so I can act first with H and then with G. H acting on X is the identity on X because H is in the stabilizer. So this is just X, and G acting on X is X because G is in the stabilizer. So here we used that H is in the stabilizer, and here that G is in the stabilizer. Therefore, GH also fixes X, and therefore GH is in the stabilizer. So the stabilizer is closed, it has identity, it's closed under inversion, and it's closed under multiplication. Therefore, the stabilizer is a subgroup of G, which is what I wanted to show. Great. So what's next? Next, we're going to prove what we call the orbit stabilizer theorem. I'm going to see some examples. And then after that, we're going to prove what we call the class equation, which will have all sorts of applications, including Cauchy's theorem, including the Sylow theorems. So we'll do that next time. Hasta la vista.